Welcome to this problem-solving session. Today, we'll explore a fascinating problem titled Minimum Number of Swaps to Make the Binary String Alternating. This problem challenges us to transform a binary string into an alternating pattern with the fewest swaps possible. Let's dive in and break it down step by step. In this problem, you are given a binary string S that consists of only the characters 0 and 1. A binary string is considered alternating if no two adjacent characters are the same. For example, strings like 0101, 1010, and even a single character string like 0 are alternating because they follow this rule. On the other hand, strings like 2000 foot, 110, or 1111 are not alternating because they contain adjacent characters that are the same. To solve this, you are allowed to swap any two characters in the string, and your task is to find the minimum number of swaps needed to make the string alternating. However, if it's impossible to rearrange the characters into an alternating pattern, you should return -1. The input will always be a binary string S where the length of S is between 1 and 100,000, and the output will be an integer representing the minimum swaps required or -1 if it's not feasible. Let's look at some examples to better understand the problem. For the input string S equals 111000, the output is 1. Here's why. One possible way to make the string alternating is to swap the second character, which is 1, with the fifth character, which is 0. This results in the string 101010, which is now alternating. Since only one swap is required, the output is 1. Another example is when S equals 010. In this case, the output is 0 because the string is already alternating. No swaps are needed here, so the answer is simply 0. Now, consider the input S equals 1110. The output for this case is -1. This is because it is not possible to rearrange the characters to form an alternating string. If you look closely, there are 3 ones and only 1 0, so the counts of ones and zeros differ by more than 1. This imbalance makes it impossible to achieve a valid alternating pattern, so the result is -1. This shows that the feasibility of creating an alternating string depends heavily on the counts of zeros and ones in the input string. If the difference in their counts exceeds 1, the task becomes impossible. Let's now consider some edge cases to clarify the problem further. If the string has only one character, such as S equals 0 or S equals 1, the string is already alternating, so the output is 0. Another important edge case is when the counts of zeros and ones differ by more than 1. For instance, if S equals 11100000, you should return -1 because it's impossible to balance the counts to create an alternating arrangement. For large inputs, such as strings with lengths close to 100,000, the solution must handle these efficiently to avoid timeouts. For example, an already alternating string like S equals 100,1010 should directly return 0 since no swaps are needed. The overall approach involves first checking if the counts of zeros and ones make it feasible to create an alternating string. If it is feasible, the next step is to calculate the minimum swaps needed by considering mismatches in the two possible alternating patterns, starting with 0 or starting with 1. To solve the problem of transforming a binary string into an alternating binary string with the fewest swaps, we first need to understand what an alternating binary string is. It's a string that alternates between 0 and 1, such as 0101 or 1010. Now, one potential way to approach this problem is with brute force. The intuition here is to try all possible swaps to generate alternating strings and then calculate the number of swaps needed for each case, ultimately returning the minimum. However, this approach is very inefficient because for each possible target pattern, we would need to iterate through the string to count mismatches, resulting in a time complexity of O(n)². This makes brute force infeasible for larger strings. Instead, we can use a more optimal strategy that focuses on counting mismatches against the two valid alternating patterns and calculating the swaps mathematically. This approach avoids simulating swaps directly, making it far more efficient. Now, let's break down the key observations that make this optimal approach work. First, there are always two valid alternating patterns for any binary string, 010101 and 100,1010. For a string to be converted into one of these patterns, the counts of zeros and ones within the string must differ by at most 1. For instance, in a string of length 6, we can have 3 zeros and 3 ones, but it's impossible to achieve an alternating pattern if the counts are 5 zeros and 1 1. Another observation is that mismatches occur when the character at an even indexed position doesn't match the expected character in the target pattern. The number of swaps can then be calculated as half the mismatches at even and odd positions. To implement this, we first count the total occurrences of 0 and 1. If the difference between these counts exceeds 1, the transformation is impossible, and we return -1. Otherwise, we calculate the mismatches for both valid patterns. Depending on whether the string has more zeros or ones, we determine which pattern is valid and compute the swaps accordingly. If the counts are equal, we take the minimum swaps required to match either pattern. In the implementation, we start by counting the occurrences of 0 and 1. If the absolute difference between these counts is greater than 1, we immediately return -1, as it's not possible to convert the string to an alternating pattern. Next, we define a helper function to calculate mismatches by comparing the input string to a given target pattern. We then construct the two valid patterns programmatically, one starting with 0 and the other with 1. Depending on whether the string has more zeros, more ones, or equal numbers of both, we calculate the required swaps. If there are more zeros, only the 010101 pattern is valid. If there are more ones, only the 1001010 pattern is valid. When the counts are equal, we calculate swaps for both patterns and return the minimum. This implementation is efficient, with a time complexity of O(n), because we only need to iterate through the string to count mismatches, and a space complexity of O(n), due to the construction of the target patterns. However, the space usage can be reduced to O(1) by calculating mismatches directly based on indices without explicitly storing the patterns. When comparing the different approaches, we see clear trade-offs. The brute force method, while simpler to conceptualize, is computationally infeasible due to its quadratic time complexity, making it unsuitable for large inputs. On the other hand, the optimal approach, though slightly more complex to implement, scales efficiently with the input size and leverages key insights about parity and mismatches. Additionally, while pre-computing the alternating patterns can save computation time, it increases memory usage, which may be a concern for very large strings. Overall, the chosen optimal approach balances clarity, efficiency, and scalability. By focusing on mismatch counting and avoiding redundant computations, we achieve a solution that is both elegant and robust, making it the best choice for this problem. In this problem, we are tasked with finding the minimum number of swaps needed to transform a given binary string into an alternating binary string. Remember, an alternating binary string is one where the characters alternate between 0 and 1, such as 0101 or 1010. To approach this, we first need to understand that there are only two valid alternating patterns for a binary string of length n. The first pattern starts with 0, creating a sequence like 010101, and the second pattern starts with 1, resulting in 1001010. Next, we need to count mismatches for both patterns. As we traverse the string, we compare each character with the corresponding character in both patterns. To do this, we maintain two counters, mismatch_0, which tracks mismatches if the string were to match the first pattern, and mismatch_1, which tracks mismatches for the second pattern. At each index, we check if the character matches the expected one in pattern 1 and increment mismatch_0 if it doesn't. Similarly, we check against pattern 2 and increment mismatch_1 if there's a mismatch there. After counting mismatches, we need to determine if transforming the string into an alternating binary string is even feasible. For this transformation to be possible, the string must have a balanced distribution of zeros and ones. Specifically, for even-length strings, the counts of 0 and 1 must be equal. For odd-length strings, the difference between the counts of 0 and 1 can be at most 1. To check this, we calculate the total numbers of zeros and ones in the string using count_0 and count_1. If the difference between these counts exceeds 1, it means the transformation is not feasible, and we return -1. On the other hand, if the counts satisfy this condition, we proceed to calculate the minimum swaps required. Since a swap involves exchanging a misplaced 0 with a misplaced 1, the number of swaps needed for each pattern is equal to half the number of mismatches. If count_0 is greater than count_1, we must choose pattern 1. Conversely, if count_1 is greater, we choose pattern 2. If the counts are equal, we simply select the pattern that results in fewer swaps. Finally, once we've determined the feasible pattern and calculated the mismatches, we return the result. Specifically, we return the minimum number of swaps required to transform the string into an alternating binary string. If transformation was deemed impossible during the feasibility check, we return -1 instead. To summarize the key insights here, our solution leverages the fact that there are only two fixed alternating patterns to compare against, making the approach highly efficient. By counting mismatches for these two patterns, we can directly determine the number of misplaced characters and calculate the swaps required. Additionally, performing an early feasibility check ensures that we avoid unnecessary computation if the string cannot be transformed. The algorithm uses simple integer counters for tracking mismatches in character counts, and direct string comparisons make the implementation straightforward without requiring additional data structures. Let's analyze the complexity of this approach. The time complexity is O(n), where n is the length of the binary string. This is because we only traverse the string once to count mismatches and check feasibility. The space complexity is O(1), since we only use a few integer counters and do not need any additional data structures. Now, let's walk through an example to see this algorithm in action. Suppose the input binary string is 111,000. First, we generate the two valid alternating patterns based on the length of the string. Pattern 1 is 010101, which starts with 0, and pattern 2 is 101,010, which starts with 1. Next, we count mismatches by comparing the input string with each pattern. When comparing with pattern 1, we find that 4 characters are mismatched, so mismatch_0 equals 4. When comparing with pattern 2, we find 2 mismatches, so mismatch_1 equals 2. Now, we move on to check the feasibility of transforming the string. By counting the total number of zeros and ones, we find that count_0 equals 3 and count_1 also equals 3. Since these counts are balanced, the transformation is feasible. Next, we calculate the number of swaps needed for each pattern. For pattern 1, the swaps required are mismatch_0/2, which is 4 divided by 2, resulting in 2 swaps. For pattern 2, the swaps required are mismatch_1/2, which is 2 divided by 2, resulting in 1 swap. Since pattern 2 requires fewer swaps, we choose it, and the minimum number of swaps needed is 1. Therefore, the output for this example is 1, meaning 1 swap is required to transform 111,000 into an alternating binary string. Here, we define a Python class called solution with a method minswaps that takes a binary string s as input. The first step is to determine the length of the string n, along with the counts of zeros and ones using the count method. These counts are essential because if the absolute difference between the number of zeros and ones exceeds 1, it becomes impossible to alternate the string in the desired fashion. In such cases, we immediately return -1. Next, we define a helper function calculate_swaps, which takes a target pattern as input and calculates how many swaps are needed to make the input string match that pattern. This is done by iterating over the characters in the string and comparing them to the corresponding characters in the target pattern. Whenever there's a mismatch, we increment a swap counter. Since each swap fixes 2 mismatches, we divide the total count by 2 before returning it. Finally, we construct 2 possible alternating patterns, pattern_1, which starts with 0, and pattern_2, which starts with 1. These patterns are generated based on the length of the input string, ensuring they alternate correctly and account for odd-length strings if needed. If the count of zeros is greater than the count of ones, we know the valid alternating string must start with 0, so we calculate the swaps required to match pattern_1 and return the result. Similarly, if the count of ones is greater, the valid alternating string must start with 1, so we calculate and return the swaps for pattern_2. However, if the counts of zeros and ones are equal, both patterns are valid options. In this case, we compute the swaps required for both pattern_1 and pattern_2 and return the smaller of the two values. This ensures we minimize the number of swaps needed to transform the input string into an alternating binary string. Here, we start by defining a Java class called solution and a method named minswaps, which takes a binary string s as input. The first step is to determine the length of the string and initialize 2 counters, count 0 and count 1, to 0. These will track the number of zeros and ones in the string, respectively. Next, we iterate through each character of the string using a for each loop. If the character is 0, we increment count 0, and if it's 1, we increment count 1. After counting the zeros and ones, we check if the absolute difference between count 0 and count 1 is greater than 1. If it is, that means it's impossible to rearrange the string into an alternating pattern, so we return -1. Finally, we define a helper method, calculateSwaps, which determines the number of swaps needed to transform the string into a specific alternating pattern. It takes the string and the desired starting character, firstchar, as inputs and calculates the swaps required by comparing each character of the string with the expected alternating pattern. Inside the calculateSwaps method, we initialize a variable called swaps to track the number of mismatches. For each position in the string, we calculate the expected character based on whether the index is even or odd. If the current character in the string does not match the expected character, we increment the swaps counter. At the end of the loop, we divide the swaps by 2, as each swap resolves 2 mismatches, and return the result. Returning to the main minswaps method, we now decide the starting character for the alternating pattern based on the counts of zeros and ones. If count 0 is greater, the pattern must start with 0, so we call calculateSwaps with 0 as the starting character. Similarly, if count 1 is greater, we call calculateSwaps with 1. If the counts are equal, we calculate the swaps for both patterns and return the minimum of the two values, ensuring we determine the fewest swaps needed to make the string alternating. The problem we're tackling here involves transforming a binary string into an alternating binary string with the minimum number of swaps. An alternating binary string is one where the digits alternate between 0 and 1, such as 0101 or 1010. If it's not possible to achieve this transformation, the function should return -1. Let's start with the first example where the input string is s equals 111000. First, we initialize some basic variables. We find that the length of the string is 6, and we count the number of 0s and 1s in the string. Both count_0 and count_1 are 3, so the absolute difference between the two counts is 0. Since this difference is less than or equal to 1, it's possible to create an alternating binary string. Next, we generate two possible alternating patterns. The first pattern, starting with a 0, is 010101. The second pattern, starting with a 1, is 101010. Now, we calculate the number of swaps needed to transform the input string s into each of these patterns. Let's start with pattern_1, which begins with a 0. We compare s to pattern_1 and find mismatches at indices 0, 1, and 2. That gives us a total of 3 mismatches. To determine the number of swaps, we divide the mismatches by 2, since each swap fixes 2 mismatches. This results in 3///2 equals 1 swap. Next, for pattern_2, which begins with a 1, we find mismatches at indices 3, 4, and 5. Again, we have 3 mismatches, which also require 3///2 equals 1 swap. Since both patterns require exactly 1 swap, the minimum number of swaps is 1. Therefore, we return 1 as the result. In this second example, the input string is s equals 1110. We begin by initializing and counting the characters. The length of the string is 4, with count_0 equal to 1 and count_1 equal to 3. Here, the absolute difference between count_0 and count_1 is 2, which is greater than 1. This means it's not possible to transform the string into an alternating binary string, as the imbalance between 0s and 1s is too large. Since alternating is impossible in this case, the function simply returns -1. In the third example, the input string is s equals 1001. First, we initialize and count the characters. The length of the string is 4, with count_0 equal to 2 and count_1 also equal to 2. Since the absolute difference between count_0 and count_1 is 0, which is less than or equal to 1, it's possible to transform the string into an alternating binary string. Next, we generate the two possible alternating patterns. The first pattern, starting with a 0, is 0101. The second pattern, starting with a 1, is 1010. These patterns will help us calculate the number of swaps needed to make the transformation. To determine the number of swaps, we compare as to each pattern. For pattern underscore 1, which starts with 0, we find mismatches at indices 0 and 1, giving us a total of 2 mismatches. Dividing by 2, we find that 2/2 equals 1 swap is needed. For pattern underscore 2, which starts with 1, we find mismatches at indices 2 and 3, also resulting in 2 mismatches. Again, this requires 2/2 equals 1 swap. Since both patterns require exactly 1 swap, the minimum number of swaps is 1. Therefore, the function returns 1 as the result. Here, we start by analyzing the time complexity of our solution step by step. The first step involves counting the number of zeros and ones in the binary string. This is achieved using the count method, which scans through the entire string. Since the method is called twice, once for 0 and once for 1, each call takes n, where n is the length of the string. Therefore, the total time complexity for this step is n. Next, we generate two alternating binary string patterns, pattern underscore 1 and pattern underscore 2. Each pattern is created to match the length of the input string, and since this involves constructing strings of length n, the time complexity for generating both patterns is n. Thus, the time complexity for counting and pattern generation combined is n. Now, let's move on to the step of calculating swaps. The calculate underscore swaps function takes the input string and compares it against one of the generated patterns. This involves iterating over the string, comparing each character with the corresponding character in the pattern, which takes 1 per comparison. Since there are n characters in the string, one call to calculate underscore swaps has a time complexity of n. In the worst case, we perform this operation twice, once for each pattern, so the total time complexity for swap calculations is n. Finally, the decision-making step, where we compare the counts of zeros and ones and choose the best pattern, involves only constant time operations, or O1. When we sum the contributions of counting, pattern generation, and swap calculations, the total time complexity of the solution is n, making it very efficient. Turning to space complexity, the input string s of length n is passed to the function, which occupies n space. Additionally, we generate two patterns, pattern underscore 1 and pattern underscore 2, each of which is also of length n. Together, these patterns require n plus n equals n space. Apart from these, the solution uses a few auxiliary variables, such as count underscore 0, count underscore 1, and swaps, which require constant space, or O1. Since the space used by the input and the patterns dominates the overall space usage, the total space complexity of the solution is n. This ensures that the solution is not just fast but also memory efficient. To better understand the efficiency of our solution, let's analyze its behavior in different cases. In the best case, the string is already alternating, meaning only minimal swaps are needed. However, even in this scenario, the complexity remains n, because we still need to count the characters and generate the patterns. In the average case, the string is balanced in terms of the number of zeros and ones, but it is not alternating. Here, we calculate swaps for both patterns, which still results in a time complexity of n. In the worst case, the string has a significant imbalance between zeros and ones, making it impossible to alternate. Even in this situation, the complexity remains n due to the counting step. By comparison, a brute force approach would involve generating all permutations of the string with the same number of zeros and ones, checking each permutation for alternating patterns, and calculating swaps. This approach would have a factorial time complexity, n, which is far less practical than our optimized solution. Our optimized approach avoids the inefficiencies of brute force by directly calculating swaps for the two possible alternating patterns, reducing the time complexity to n. To confirm this mathematically, we note that counting operations like s.count, 0, scan the string once, which is n. Generating patterns involves creating strings of length n, which takes n. The calculate underscore swaps function performs a single pass through the string, requiring n. When we sum these contributions, the total time complexity is n. For space complexity, the input string and the generated patterns dominate memory usage, each requiring n. Thus, the overall space complexity is also n. This makes our solution optimal in both time and space, providing an efficient and scalable approach to the problem. When solving this problem, there are several common mistakes to watch out for. First, always remember that a binary string can alternate in two ways, 0101 or 1010. It's easy to overlook this and only calculate swaps for one pattern, but you need to check both and choose the minimum. Another frequent oversight involves ignoring edge cases. For example, strings that consist entirely of zeros or ones, or even strings of length 1. These special cases can lead to incorrect assumptions or runtime errors if not handled properly. Additionally, it's crucial to understand that each misplaced 0 or 1 only needs to be swapped once. If you're counting both ends of a swap, you might accidentally double the required operations, which will inflate your result unnecessarily. Also, remember that swaps can only be performed between adjacent characters. Some solutions incorrectly assume unrestricted swaps, which is not valid under the problem's constraints. Lastly, be mindful of efficiency. Iterating over the string multiple times can lead to a time complexity of O(n) squared, or worse. To optimize, aim for a single pass using counters, which brings the complexity down to O(n). This problem is often used in interviews to test your ability to identify patterns, such as alternating strings, and to optimize your solution by minimizing mismatches. A good practice during an interview is to discuss edge cases with your interviewer. For instance, what happens if the input string is empty or has an odd length? Bringing up these scenarios shows attention to detail, which is highly valued. Additionally, consider the trade-offs between readability and performance. For example, a brute force simulation approach might be easier to explain step by step, but it sacrifices efficiency. You should also be prepared to adapt your solution to handle variations of the problem. These might include non-binary strings or additional constraints, like assigning different costs to swaps. Demonstrating flexibility in your approach will leave a strong impression. If you're looking to deepen your understanding, there are several related problems that you can explore. These include LeetCode 1249, which focuses on removing the minimum number of characters to make parentheses valid, and LeetCode 1151, which involves grouping all the ones together with the minimum number of swaps. Of course, LeetCode 1864, the problem we're discussing, is a direct example, and LeetCode 921 challenges you to add the minimum number of parentheses to make a string valid. Exploring these problems can help you identify recurring patterns and techniques. One effective alternative approach for this problem is the two-pointer method. In this approach, you use two pointers to count mismatches for both 0101 and 1010 patterns. This method is efficient with a linear time complexity of O(n), but it requires careful index management to ensure accuracy. Another approach to consider is brute force simulation. This involves simulating the swaps for both alternating patterns and counting the required operations. While it's easier to implement and explain, it's not efficient, often resulting in a time complexity of O(n) squared, or worse. A more optimized method is the greedy counting approach, where you count misplaced zeros and ones in a single pass. This technique is both fast and space efficient, with a time complexity of O(n). However, it can be trickier to debug due to its compact nature. For those comfortable with advanced methods, bit manipulation offers a unique solution. Here, you represent the string as a binary number and manipulate bits to determine mismatches. While this approach is highly efficient, it's less intuitive and can be harder to articulate during an interview. Choosing the right approach often depends on the balance between efficiency and clarity in your explanation. Great job following along. To summarize, we tackled the minimum number of swaps to make the binary string alternating problem by analyzing different approaches and considering edge cases. Remember the importance of optimization and edge case testing in your coding practice. Thanks for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!